All right, so this is the next episode for digging into the SQLite internals. There's some really kind of interesting things that happened last week, which is that Julia Evans has been writing all this really cool SQL information. She's been doing exercises and some internal stuff and kind of putting out these little releases of stuff from her upcoming zine. And then this one sort of showed up, and I thought this was really kind of cool to start with because this is where I thought I might start. So this post, SQL queries don't start with select, gives this fantastic diagram of what is fundamentally the general order of a SQL query, right? And the surprising thing here is you've got from and join at the top, where you normally would think the select would happen at the top. That gets funneled into a filter, so that's where. Then those get partitioned into groups. Then a having filter is called, which allows you to filter on the individual groups and the aggregations related to those groups. Then you have select, and she's added this kind of handy thing here which says that window functions happen here. I won't go into window functions if you're not familiar with them, because she's really giving some really good, let's see here. She actually has one that explains window functions that's recent. But what's really cool about this is that then it goes into an order by, so it actually orders the rows, and then there's a limit, and the limit just kind of cuts down, right, again. So if we go back here, there is this query planning section of the SQLite documentation, which is actually it's a really quick read, and it gives a great explanation of how queries, many different types of queries would be executed. And the nice thing about this as well is it includes into the picture indices, right? So you might have some index here where you want to select price from fruit for sale, where fruit equals orange and state equals California, and it'll give an example of first how it's doing its thing and searching off of the index, and then it's going off into the table, and at the table it's using the information it deduced from the index, so that here we have the row ID 1 and row ID 23, and then it will fetch those rows. The difference between row ID and a primary key is effectively that a primary key is instigated on the creation by the, I don't know what you would call it, by the user, right? And the row ID, if there is no primary key, is something that SQLite keeps internally. In fact, it's very possible that row ID always exists, and that the primary key, just when that gets wedged in, everything uses that if there is a primary key. Cool, so both of those things I really recommend reading, and I thought I would go into some query planning stuff, but there's a bit of this that's sort of tangentially related. I say tangentially because it's not, it's related, but it's not one-to-one, right? So the query planner is how stuff gets prepared to be fed into the bytecode engine. And the purpose of the bytecode engine, which is, it is a virtual machine. There's actually a name that it used to have. So if we go back, I was looking around here before, there's this piece of documentation on SQLite's website, and it says the virtual database engine of SQLite, and you'll see obsolete documentation warning. So then you go up here to bytecode engine, and you look at VDBE. Historically, the bytecode engine in SQLite is called the Virtual Database Engine, or VDBE. This website uses the terms bytecode engine, VDBE, virtual machine, and bytecode virtual machine interchangeably, as they all mean the same thing. So the gist is that the virtual machine is taking this prepared plan and then just executing stuff. And in fact, if we go to the table of contents, you'll see that the bulk of why this document looks so big is because at the bottom here in section 4, there is a huge list of all the operations and documentations about those operations. And this is kind of interesting to sort of skim through to see what the virtual machine is providing. Let's go back up. The most interesting bit I thought that would help us today, if we dig into this, was section 3, viewing the bytecode. And you'll see that when you run and explain on a SQLite database, so you'll see here that it runs explain, delete from table 1 where 2 is less than 20. What you get out is a dump of the bytecode that will be fed into it. And apparently there's some bit in here about how this indentation won't be generated in anything other than the, won't be rendered in anything other than the shell. But this bit is what I was driving at, which is when SQLite is compiled with the SQLite debug compile time option, which we'll click on that, right? Extra pragma commands are available that are useful for debugging and for exploring the operation of the VDBE. So that's cool, right? That means we can, actually I don't need to go there. It's the pragma parser trace, add opt trace, debug, listing, and trace for VDBE. So we can see what the parser is doing. We can see VDBE related stuff, and I think the one that interests me the most is getting a dump of the bytecode for some really trivial thing, and then also seeing this VDBE trace thing. So we need to turn on this SQLite debug thing. So first let's get going. What was the file name that we were working in? So as a reminder of where we were before, previously we got everything building, and then after we got it building, we kind of started tweaking the shell just to sort of see where things were working, and that helped us locate the main entry point function into the shell, which we can look at today as well, which was shell, shell C in? This one. Yeah, so open that up in a new thing. In fact, we'll put that in a new tab. Now, the other thing that we want to open is we want to open, what is it? We want to open, let's just look for that pragma or that definition, define, SQLite debug. Okay. I only want C files, right? And I only want to see the files themselves. Okay, so it's in a lot of them. So one thing that we can do, let's open up the amalgam. And I actually, one question I have is, when we build this, is this going to replace the amalgam file, right? So what was the amalgam called again? It was like SQLite 3C. Right, so if you're building SQLite 3, that requires SQLite 3C. And SQLite 3C probably has a rule of how it gets built, maybe. So let's go SQLite 3C colon. Yep. Yeah, so this has target, source, and make. And what this does is interesting. Make SQLite 3C is a TCL script. It copies the SQLite 3 extension header to the current directory, and then it copies the SQLite 3 session H thing. Yeah. So it runs this to produce a file, and that probably produces in the T source the SQLite 3 extension header and something else, this session thing. So we're gonna have to go look at this. I want not the header, but this guy. And it seems like yeah, and here's the header that gets dumped out, right? So I'm just going to read that here so I don't have to jump around too much. It's telling us that it's an amalgam that's made from many C source files. To use SQLite in other programs, you need this file, another SQLite 3H header. So we can try to look at the SQLite 3H file. So yeah, it's telling us RG begin file SQLite 3H. I'm going to have to wrap these in quotes. And begin file SQLite 3. So what we want to do is, and to give you some thought process of what's happening in my head, what we are trying to get at is we effectively want to make this change, but we want to do it in a way that isn't going to get clobbered by these scripts so that we can literally just say this, right? Which is what we had last time. So let's actually start that up now. I will start another terminal instance so we can still kind of poke around and do some searching and stuff, and we'll keep building that. We can try to look for, this is just grep with a little bit of preview inside of NeoVim. In this instance of NeoVim, I have colors turned off, but colors are a little handy because they can sort of help you parse things quickly if you need it. I'm not fussed either way. So what we're trying to find, right, is that SQLite debug one, right? And that's all over the place, but it's just checking for it. So what we want to do is one option. We can go back to that make SQLite 3 thing. And we can actually, you'll notice that it has some defines in here. And we can be very, very cheeky. And we can just say define SQLite debug 1. Right. What that is going to do is, because that's in tool, that's not going to change. But if I go to source shelling, let's just save that, right? And then here's a cool thing, control, well, it's supposed to be a cool thing. There you go. Implicit declaration of functions. It seems like something I've done has caused a warning to go off. But it's possible. So another thing that we had done was make a little database, right? I don't know, since we don't have get, I can't quickly kind of grok this. Where is it? Where is it? Where is it? I may have blown it away. I'm not sure. Yeah. So there is another way to do this. Sorry, that happens sometimes. So setting defines with make. And you can do it this way, right? You can say make, and then you can say what the flag is, and then that will just pass it along to everything. So that's one option we have. It's the C flags thing. That's C flags. do this? Yeah, so you can do it like that. Which, sure, why not? Let's just go back. That way we don't have to worry about anything. We'll just ensure it gets passed through. So, make clean and make SQLite debug equals. Right. So SQLite 3, remember, got set here, and then we had like a test thingy. I can't remember where we put it, but we can just make a new one. So once that builds, I'm going to run that because that's the one I actually want. And this will probably spit out heaps of output, or like what they said, so it's going to run 3 times slower having turned this on. The SQLite debug compile time option does this. SQLite debug also enables some other debugging features such as special pragma statements that turn on tracing and listing features used for troubleshooting and analysis of the VDBE in code generator. So there's also a mem debug option, which is kind of cool. The instrumented memory allocator checks for misuse of dynamically allocated memory. Examples of misuse include using memory after it's freed, writing. So it's kind of like a, I think it's like a caked in Valgrind sort of thing. That's cool. That might be kind of cool to look at. So this pragma, how do I turn on this pragma? VDBE trace boolean. Alright, pragma is intended with debugging SQLite itself. Okay, so how do I turn on any of these pragmas? Let's go to the top. Index info pragma. Okay, so you just say pragma, right? And the pragma is VDBE trace, and I don't think I have to, something else. There we go. That's better. I don't think I have to yeah, I don't think I have to set this with a number. Boolean. I think this is how we say it. Okay, so let's go back here. Okay, pragma VDBE trace equals 1. Go. Boom. That seems to have worked. Create table foo. So you go ID primary key. I don't know if I have primary key. Name OFR of 50. Cool. Tables, I think it was. Yep. Insert into foo. Name values. Okay. So this is a little bit weird because where is our I know what's up. Yeah, it's a bit annoying. I don't think the clean is cleaning files, but it may not clean the SQLite file away. I'm not totally sure if it is. So here's the bytecode dump of inserting into, and you'll see that what happens is there's always an initialization bytecode. Then we open things for write, so we open, there's this interesting comment section, which is kind of like, I think it gives some insight into the internals, right? Like, so registers being used and table names and etc. And even here's a SQLite auto index. So this is an automatic temporary index. So open write foo. SQLite auto index is opened. We have a new row ID generated. We have a string 8, Bob, halt if null, so foo.name, this is jammed in there, Bob is not null. So this is how it enforces not null checks. Affinity, I'm not sure what that is. Nup, so uniqueness check for SQLite auto index foo. That's interesting. So there's a no-op for checking there's a uniqueness, and that's probably because there might be something else that's doing that. It's a bit odd. So if we go back here to the bytecode engine, let's just quickly see what affinity says. Apply affinities to a range of P2 registers starting with P1. P4 is a string that is P2 characters long. The nth character of the string indicates the column affinity that should be used for the nth memory cell in the range. Okay, so it's a bit like memory affinity, right? Where it should go, it has been in the past. So there's scopy, inc copy, make record, no conflict, halt. There's two halts. So let's go figure out why. Exit immediately. All open cursors, etc., are closed automatically. So really quickly, the thing about halt is, okay, so the thing about the virtual engine is that there's a bit of this abstraction called a cursor. And cursors are pretty common actually because, like, I really like this example of a cursor in Rust. So, yep, cursor reps an in-memory buffer and provides it with a seek implementation. But that's for I/O. But theoretically, you can have a cursor on, you know, any kind of seekable thing, right? What's handy about this is that it sort of represents the same interface you would have with like C files of being able to seek on things and set positions and rewind and write to it, etc. So I'll give an example of it. The Rust thing uses this trait called seek. So this is actually a struct, and struct implements this property seek. And what seek does is it says seek to an offset in bytes in a stream. Cool. A seek beyond the end of a stream is allowed, but behavior is defined by the implementation. Cool. It also provides, once you've done that, like where you are in the position, the length, those are nightly features. This is experimental nightly. Yeah. And cursors are kind of similar because the idea of a cursor in SQLite or in a database is this thing that somebody described it once to me as like a finger pointing to a row in a row-oriented database. And the finger is sort of, it could go to the next one, it can go to the previous one, it can skip ahead a whole bunch, so that's sort of like seeking. And it can, you know, read in the row, right? And then kind of cast some of the things that go on, some of the result values. So the idea of this halt statement is kind of interesting that it happens twice, because generally with a virtual machine, you'd assume that halt is the last thing that the virtual machine gets. Except in this case, we're seeing that halt happens here with foo ID, right? These are the arguments and registers, I believe. So 155520 foo ID, P5 is 02. And then make record happens, index insert happens, insert this thing into foo happens, then it halts. Then a transaction starts, and it uses the statement journal as false, and then some null thing happens here. That's interesting, so let's go check that out. It is null. Write a null into registers P2. If P3 greater than P2, then also write null into register P3 and every register in between P2 and P3. So it's kind of like a clear, almost. But I also want to go back to that halt statement. P5 is a value between 0 and 4. Alright. If P5 is not 0 and P4 is null, then everything after the colon is omitted. There is an implied halt instruction inserted at the very end of the program, so a jump past the last instruction of the program is the same as executing halt. So this, oops, so that will always have a halt. But it's weird, right? So it's saying exit immediately. So for a normal halt, it should be SQLite okay, and for errors, it could be some other value, right? It could be finalized, right? P1 is the result code, so what this is saying is the result code is 1555. That's a bit odd. Oh, it's actually possible is right. Okay, so one way that we can read this right is sort of like assembly. And in assembly, not every command is going to be executed. There might be some commands that will jump, right? So it's possible that like one of these commands is taking an argument that's saying, well, if there's like this no conflict thing might jump, right? So it might say, well, if there is no conflict, then go to 13, which I think is what this argument is. And if there is a conflict, then halt with this error code. Okay, that makes sense to me. And let's just confirm that by going up here. No conflict. So if P4 is equal to 0, then register P3 holds a blob constructed by make record. So if P4 is 0, which one's P4? This one? That's not 0. If P4 is greater than 0, oh, actually, yeah, it is 0 because foo.id will be 0 at the beginning. So it's going to make a record. And then what it'll do is SQLite databases tend to have 1 indexed versus 0 indexed for rows. Yeah. Cursor P1 is on an index B tree. If the record identified by P3 and P4 contains any null value, jump immediately to P2. If all terms of the record are not null, then a check is done to determine if any row in the P1 index B tree has a matching key prefix. If there are no matches, jump immediately to P2. Okay, so let's reread that because that included jumps. If all terms of the records are not null, then a check is done to determine if any row in the P1 index B tree has a matching key prefix. If there are no matches, jump immediately to P2. So that is what might happen, is P2. If there is a match, fall through and leave the P1 cursor pointing to the matching row. So the idea is that if there is a match, right, for a null value, then we're going to halt. I think if I'm understanding it correctly. Matching key prefix. My brain's a bit out of it, so I don't think this is the highest value thing for me to be spacing out to. But, sorry. Basically the idea is, if you've got, if whatever check is happening here in no conflict, right, meaning either a null check or a uniqueness check or whatever this was, I think it was a null check or something, then if there is a problem, then fall through to a halt. And if there isn't, then jump to 13, which is that we're going to make a record. And there was also something up here about making a record too, right? So I think what's happening here is that we make a record in the index, and then once we make a record in the index, we make a record in the thing, the actual table of foo, right? And I think what happens is that this complains that foo ID is like, you know, null or something, right? Whatever this conflict issue is. Cool, so what I'm going to try to do now is I'm going to try to get this to build and get the pragma going that will let us do our thing. So we want to see what I want to know is what, so let's go back to that make file. Let's go back up to all. And part of all is going to involve, I'm just going to make a dummy one called show end. Right, it's not going to have any requirements. It's going to be phony. So let's see if I get this right. And I'm just going to dump my environment. Actually, I'll just say echo. Well, let's just see if this works first, right? SQLite 3 test DB. What was it? Temp? Test DB, yeah. SQLite 3 test DB. Okay. Now it's kind of annoying that we get no information on this, but create table foo, ID primary key, name bar call 50. Oopsie daisy. Can I please go up, or are you gonna? Interesting. So, yeah, we're not really getting much information about this. So, I don't know why the pragmas aren't working, and part of it possibly is because SQLite debug isn't being set. So, I'm going to be cheeky again. So underneath source, right? Let's close this. Let's go back up. Let's try to just run make SQLite debug 1. Nothing to be done for all. Make clean. And let's just confirm that deleted what I thought it deleted, which is that it should also clean out the SQLite 3 binary itself as well. Okay, I'm not convinced that it does. So clean. Oh wait, no, it's at the top. You can see it here, SQLite 3. Yeah, so it does clear it out. So make SQLite debug 1. Can look at some of these other ones too. Now trace might have a requirement. If it has been compiled with SQLite debug, compile time option, then VDB trace pragma can be used to cause virtual machine opcodes to be printed on standard out as if they were evaluated, as they are evaluated. Okay, so what this means for me is if that still doesn't work, what we're going to want to do is init, there was like a initialize thing, main init, there you go. And SQLite 3 initialize, and then SQLite 3 shutdown, and then some assertions. Verify uninitialized. Excuse me. So let's go back here and let's quickly kind of explore TestDB again. Okay, I don't know why this isn't persisting. Let's actually find out. Ugh, snarky responses. All right, so what I want to know is, yeah, it is using that. Okay, so we got foo now. Pragma. Days, PDB trace pragma not working. Some pragmas take effect during the SQL compilation stage, not the execution stage. Prepare step 3 finalize. Oh, excuse me. That's interesting. Okay, so my goal now is to try to get this pragma to work so that we've got some kind of output. And one thing that would help us so well, printf, yeah, that does exist. Main, init, printf, alright, so let's I'm gonna get this going. That should effectively do the same thing. I'm gonna close that. Waiting for this to build over and over again. It's probably a faster way. Trace, SQLite. Yeah, so while that's building, SQLite debug is undeclared. Right. That's interesting. So that is implicit of some interesting stuff. So SQLite debug. You'll see that we've got ext stuff using it. T-source, autoconf, again T-source stuff using it. Above this we should eventually get source stuff that's using it. This is a big one. This might actually be the amalgam. SQLite 3C has it, if SQLite 3. Alright, so let's go BDBE trace. BDBE trace in SQLite C, 3C. Here's pragma test. Ah, VDBE trace on. That's probably why. Okay, that makes sense then. So we're going to wait for that to build. And once it does, we can put this pragma instead that says VDB trace is on. Now, if that's still not working, I'm suspect that the internals are mangling something. In which case, we can go back here and we can kind of ask, you know, put it up in the header, top level header. Excuse me. Ah, cool. Pragma VDBE trace equals on. Okay. Tables, nothing. So again, create table 2 where, sorry, ID primary key, and then right, and then we'll say select star from true. It's really annoying. You get no feedback. Also, I don't think it's just that, right? Like if you look at these, they've got zeros and stuff, ons, capitals, VDB tree, trace with 1, with exec SQL. Doesn't make a whole lot of sense. Although this is interesting. Test TK. Ticket 3461. Yes, this creates a table and it inserts the values. And and they're actually commented out. Right, so somebody was doing some work and they wanted to know what was going on, so they turned on the pragmas. Okay, so let's head back. Let's try to get this working differently. Yeah, I think what we have to do is this. And then we go shell in, save that to trigger our call. It's interesting because when you turn on SQLite debug, you start to get some warnings. So one of them is an implicit declaration of function SQLite 3 mutex held. And I don't know if warnings all is on. This is because let's go back to the make file. Yeah, so the only interesting. It's not running wall, where, or pedantic. But it is dying. There are some things here like OS Unix, warnings, warning options, shadow, wall, extra, pedantic errors, no long. So this, I don't think this generated anything actually, but we can quickly find out by seeing if the SQLite 3 binary is there. Bam! We're finally in the game. Okay. What that did was it not only turned on VDB trace, but it also started dumping stuff. So some of the other things that, so yeah, select star from foo, right? And this is as it executes. So if I say explain select star from foo, I expect to see something very similar. So init, transaction, table lock, go to open read, explain, rewind, and halt. Okay, so I think this is explain is part of the VDB trace, possibly, but I think it's one by one. So in this case, we actually see some of these indentations. So we initialize, then we open read, then we explain, then we rewind. So we have column, result row, next halt, transaction, table lock, and go to. So that's all very kind of nice and interesting, but the thing that we really care about is why did we come here today? So let me just double check that. So we've seen a bit of like the virtual machine. We're dumping bytecode. We're tracing how queries get executed. We've looked a bit into some of the stuff that goes on inside of the engine. We haven't yet explored where we were last time, which is basically how does the shell start up? But I think what's a bit more interesting is trying to get a sense of, since we're already in the guts of this, right? Not going that route, which is very top down, and going the other route with the VDB itself. So VDB-EC is what I will probably start with. If we go back up here and go to some of these other ones too that might be kind of interesting to turn on. There's this listing one. Oh, so it'll show all the opcodes that it's been compiled with. Don't care about that. Add op trace, listing, and VDB trace. So what is add op trace? Add op trace fragment can be used to cause a complete VDB opcodes to be displayed as they are created during code generation. That's interesting. Okay. There's this parser trace. So I might turn that on, and I might turn the add op trace on. So pragma VDB add op trace. Oops. Let's do that again. Okay. Cool. And the other thing we wanted to turn on was, what was it? Parser trace. Cool. So yeah, select star from foo. Okay, so now we got a bunch of information here. All this stuff that's going on. So you have select star from foo, input select in state 0, shift select. So this is all the parser doing its thing and breaking down the select into what it needs to. It's going across different states and stuff. Yeah. I'm assuming some of these, yeah, parser, then shift command. So it's reducing these labels. The VDBE is doing a couple of things already. And then it's hard to tell what is the op trace stuff and what is not. So pragma add op trace 0, pragma parser trace 0. Just gonna turn this off for now. Cool. That makes me pretty happy. I'm pretty happy with just leaving VDBE trace on. What I want is just a kind of light guide on the virtual machine. So VDBE API-C. What other VDBE stuff do we get here? bytecode engine. So VDVE-C and VDVE API are the ones that we care about. So let's look at this one first, right? You'll see that like also an int, apply numeric affinity, apply affinity, value numeric type. So this is kind of interesting. One of the things that Julia Evans mentioned she has actually a series of blog posts that I was reading over the weekend about how SQLite works. There's 1 and 2 of them. I think there might be a third. First one, she explains B trees and pages and how pages and B trees are kind of tied together when it comes to databases as a data structure. And I believe Rust's B tree map is similar. It's the same data structure. And it was either this one or there was a second one. Here we go, B trees on disk. Yeah, so it's really neat to see. Let me actually increase the size of this. It's really neat to see it doing the binary search for 99001 inside each page. I couldn't quite figure out how to get it to print out the comparisons it was doing when looking up 1000 in the index B tree, because it does some weird function pointer magic to do comparisons. So I thought it might be kind of neat to try to find that and look ourselves and see what exactly that is. So I mentioned that because this looks somewhat similar. Because SQLite is a dynamically typed thing, right? Virtual machine. The thing about it is that it's probably going to be doing some funky sort of C casting stuff to get sort of blobby stuff on disk that's just raw data, raw binary data, and then saying, well, I want to interpret that as if it were a numeric type because that's what I have stored for this schema. And I assume that's what these sort of functions are. This comment says that it says, try to convert the type of a function argument or a result column into a numeric representation using either integer or real, whichever is appropriate, but only do the conversion if it is possible without loss of information, and return the revised type of the argument. So that's that's interesting. SQLite 3 value type is retrieved. So we have the E-type, as that's called here. If it is text, then interestingly, we do this memcast of pval, right? Turn it into a memory thing, try to apply some numeric affinity to it, and then we get the value type here, which is the E-type, after we've casted it to pval. Or we get it again. I think there's probably something going on here. And then we return the type. So this is trying to get the type off of things, not necessarily the value. There's no casting of the raw value per se, except here. This function, here we are, tries to convert a value into a numeric representation if we could do so without loss of information. Yeah, interesting. There's a lot to take in here. Fundamentally though, what we want to do is maybe trace ourselves, like how Julia Evans did with her print statements, a little bit better, because this is nice and everything, and we might get some feedback on, so there's like register trace stuff, right? And that's probably what's going on. This is how registers are traced. This looks like a VDBE trace, yeah. Flags and VDBE trace if register trace RM. So register trace is called. And register trace has an I register and a memory thing P. and it just shows that memtrace print printf with a new line, and then SQLite 3 v2b check mem invariant. So there's a whole tracing system built up here to kind of slip in. There's a lot of casting and struct accesses behind pointers. There's casting between mems and the SQLite 3 value structs. SQLite 3 v2b exec though is what I was looking for. So this is execute as much of a v2b program as we can. This is the core of the SQLite 3 step. It's got all the arguments laid out for us. And SQLite 3 v2b enter. Go to no mem. This happens if a malloc inside a call of SQLite 3 colon text or SQLite 3 colon text 16. It failed. Right. Begin benign malloc. SQLite v2b print SQL. So this is interesting. It says if the program counter, which I'm assuming PC is 0, and the flags have v2b listing, v2b QP, and v2b trace on, right, if any of them are 1, right, are on, this won't be 0. And then it prints the SQL in this one. And then if v2b listing is on, v2b query plan. Okay. So it looks like v2b EQP equals 1. So let's start from 2. Scan table foo. So by turning this on, we've noticed that there's a query plan that will be given, which is scan table foo. That's cool. SQLite v2b trace is on. So it's telling you each of these which it's coming from. v2b query plan. And we can kind of be cool about this because we can start inserting some things in here, like insert, what was our schema of foo anyways? It was like, that was that register thing we saw. Yep. It's got a lot. Just checking out the schema of foo. I actually want to see the schema. It's too much output. Okay, where is it? I think it was an int. I think we called it select or something. I'm going to cheat. I'm going to say create table bar ID primary foo name bar 50 not null. Right, and then we're going to say insert into. Oh wait, did that go down? Yeah, bars there. So insert into bar name values John. I'm just gonna redo that a whole bunch of times. I can't seem to go up or down in the history of the thing. I don't know if I have to enable it. So let's do this. Select insert into bar name values Bob. I'm forgetting I need single quotes actually. Select star from Bob. So yeah, you got Bob, John. Now if this is kind of interesting because it's just going to scan table bar. But if we say create index bar index name on, let's call it bar name, on name, bar.name, what is it here? Create index bar name on bar. I think might be the syntax, yeah. Select star, select bar from bar where name equals blank. And you see the query plan, search table bar using index bar name equals the thing, right?
Which one?
Ugh. And what we're going to find is that it used the index, so here's the output of the thing. It initialized, it did the transaction, it did some table locking, it opened bar name. This jump is interesting. It's also interesting that we have these numbers here and that they're out of order. Search table bar using index bar name is blah. This is the explain. And this is probably happening because we turned the other one on, right? The other pragma. T4 John 8, so seek greater than equal to, key is 1. Deferred seek, move 0 to row dot row ID 1 if needed. Bar ID, column bar name, result row output 2 and 3, so it is collecting the result row here. Null, S for John. So this is kind of interesting. I wonder if it doesn't have this, if it kind of has commas, if they're not positional. I'm assuming this is positional. What else? SQLite VDB trace. So that's interesting, right? And if we just take a moment from hacking and kind of think about what we've accomplished for a second, we've sort of seen how the debug instrumentation gets set up. We found the entry point for the VDB, for the bytecode engine, I should call it, because that seems more appropriate. There's a whole bunch of assertions. So this is something that I'll kind of divulge into for a second. There is this idea in C called assertion, assertion-driven testing or assertion-based programming. And the idea sort of comes about with Golang panics and Rust panics and etc. The idea is that while debugging, or while you're able to change the code, you put in assertions that crash the program if not met. So if we said that, like down here, that 1 is equal to 1, and at any point in time in the world that became wrong, where that evaluated false, the program kind of collapses. And there's an interesting article I wanted to give a workshop about this last year, and then got kind of fuddled up doing it, and I've been working on a blog post sort of explaining it. But if you think about assertions, or even some people call them properties and property-based testing, as kind of the core unit of thing, and that it doesn't really matter what the form is, you're just sort of manipulating the exterior of how that assertion is coming through, or assertions. It's totally fine to have multiple of them, in my opinion. And that's great, and you're automating it, and you're putting it into an environment that gives you some sanity while you develop, right? And the point about assertion-driven programming during a debug mode, something like SQLite, is that in this case, if any of these sort of like core invariants are broken, then we know something is horribly wrong. What is an invariant? An invariant is something that must be upheld no matter what, right? So an invariant is kind of like a property of a system. Effectively, the invariant says, here is this thing. Maybe like X always has to equal blue inside of some context where X is handed in. Like we create X. So the difference between an invariant and something that's like, it tends to be 3 terms that are sort of passed around, right? There's invariant, precondition, and postcondition. And these terms are taken from what's known as axiomatic semantics. Or like Hoare logic. I'm probably ruining his name, but I think that's how you say it. So in axiomatic semantics, with preconditions, postconditions, and invariants, the idea is that a precondition is something that must be upheld in order for a contract to be fulfilled. So a precondition is like, if you want to call this function and you don't want garbage as the result, or you don't want terrible things to happen, you give me the right values, right? A post condition is where let's use a function as like the model, right? A post condition is like if something bad has happened in the middle of the execution of a function, then I guarantee that I will always spit out some result, right? Or I'll always, clean up resources or whatever. And an invariant is fundamentally this idea that no matter what, independent upon external influences or things that go on inside of me as a function, I will always uphold this. A good example of this is like loops, right? A loop invariant could be things like the index of a loop always increases by 1 for every single step of the loop. This all might seem like gobbledygook for a second, but there's some really powerful ways of thinking that come with kind of adopting this mindset and just learning about it. So in another video, I might talk about that. But these assertions don't do anything, and part of the reason why SQLite documentation is telling you that it gets a lot slower is because these assertions are being run at runtime every single time we do any of these things, right? Part of the kind of gist for seeing the rest of this function is I think this closes it off actually. There's a big goto in here with a case. If we go back up here, I just want to see how big this function, this main one, is before we kind of stop. Let's see here. SQLite exec, big argument list, this guy. So this went down to the bottom of the document. Yeah. So kind of what happens is there's all this setup, right? And then we get to this switch statement, which is the opcode. And the way that this whole thing works as execution is it just looks at these opcodes and then it runs stuff, right? So it's checking for an interrupt. Is it the op go sub? Is it jump to P2, right? Which is something else. This is a label that we would go to if needed. Here's the op return, op init coroutine, end coroutine, op yield, halted null. All of this stuff maps one-to-one with that big table of operation codes that we saw. And in fact, whatever that listing was for listing, yeah, this one, this listing print op thing, what is it? Oh, it's going across all of the number of options in the prepared statement, and it's getting them off of the prepared statement P. And if we go up and find what P is, P in, P out, P. All right. So here's P, and I want to find out where P gets set. P, A, N. Here we go. So VDBE exec takes one argument, which is a VDBE struct thing, and it's a pointer named P. So this VDBE thing, right, struct VDBE, struct VDBE. Let's go up one. This is all the stuff we have, and we saw that nop thing, right? Number of instructions in the program, and then if we go back quickly, listing, you'll see that it goes across each option, and then it goes AOP, which is this guy, space to hold the virtual machines program. So this is a virtual table to all the ops that have been given inside of this VDBE. And the next piece of this puzzle that I want to just sort of cinch off before we leave is this told us that SQLite 3-step was the big kind of driver of this function, right? So let's go find that function. SQLite 3-step. Now, let's close this. Let's wrap this quotes. My bad. want is only want C files. We want to glob out everything that says test, so not test. That's right. This is a bit funky because the bang here will get picked up by our shell. So I need to do single quotes so that it's not expanded. And I think what we want to do is we specifically want to look at the source directory. So I'm trying to see where it is originally defined. It might actually be able to say control here. So there is this. I can go back to SQLite 3 step seems defined at VDBE APIC. Yeah, so let's go to that one, 3. So just to give a quick description of what happened there, I tried to find it with root grep, and then there's a bunch of calls that were kind of unclear. If I knew what the return value was, I could probably have grepped it for it a little bit better, because sometimes you can use associated text around like an identifier, this is the identifier, SQLite 3 step, right? That's the identifier. And then I can say things like, well, if I know it's a struct or if it's int or whatever, I can throw those in, and I'm more likely to find the function definition because I know that's more unique in all of the text of the program or all of the source. In this particular case, I used my tags to very quickly find it, and since there were multiple definitions, I used the tag that very clearly looked like a function definition. So it says that this is the top level implementation of SQLite 3 step. You call this to do most of the work, and if a schema error occurs, you have to call reprepare. So apparently preparing might go wrong. So we kind of know that there's a preparation stage that gets stuff ready for the virtual machine, and then that gets handed in. So this SQLite 3 step 3, VDB safety not null, mutex enter, etc. This is actually pretty quick. We have result code, SQLite OK. This is just a define, and this is probably just some number, right? So you can say, what is that? Looks like it's 0, successful result. So we're gonna go back. We have the statement. We have the P statement comes from this. So SQLite 3 statement is what the prepared statement has. And then we cast that into a VDBE pointer. So that's sort of interesting because that means these probably ought to have the same shape. So VDBE. Let's go look at this at 3. Oh man. So this is referencing the struct definition. Let's go back. So yeah, RG. SQLite 3 statement. Back up again. SQLite 3 statement. So yeah, that's our type def. So we've got the type defs here. But what I really want is the original. I want the original thing. SQLite 3 header file. Tests. Right. I'm just gonna say source just hunting for this definition. Main C has this. memd prepare seems to mention it. VDB API, right? Yeah, it's being used all over the place, but we're trying to find where the original struct is. Yeah, I'll have to kind of go looking later. It's not really the highest priority right now. Crap. So yeah, we want to go back to 3, where we were. So regardless of what this SQLite 3 statement thing is, which we can explore next time if we really want to, we're just going to kind of quickly glance at what this function does, because that sort of ties in the execution stuff into a bigger picture context. There's a counter to prevent infinite loop or of reprepares, so this is kind of like probably going to be passed somewhere, I guess. Yeah, count plus. So if the return code comes back from SQLite 3 step, which seems to be some other non-snake case name. Interesting, so this is a driver function, and this guy basically executes a statement until a row of data is ready, the statement is completely executed, or an error occurs. Yeah, cool. And it does this over and over and over again until the return code is finally equal to 0. And the count keeps increasing, and we keep retrying until some max here, right? And we can quickly kind of go look at that. So 50 retries. We reprepare. If it isn't okay, right, then, so I'm actually kind of curious, why is SQLite schema 0? That's 17. So while this is equal to 17, oddly enough, then if RC isn't equal to 0, then we've got this message here that's telling us that this handles a very particular case of error. And it does a bunch of stuff here so that an error message is available because of some concerns. SQLite 3 value text, the database is freed, there might be a malloc failure. If you don't know C, these little arrows are, it's a combination of a struct access with a pointer dereference, I believe. I believe that's the case. It's been a little while for me. Yeah, I can very quickly kind of confirm that. No, I can't. Stop recording that macro accidentally. Let's go to this one. All right, VDB. So remember how we found it last time? Right, up here we did this. So what was it? DB. This is a pointer. Yep. So let's jump back. Right. We call reset at the end. Like if this stuff didn't happen, call reset at the end. assert something's expired is equal to false. And then SQLite 3 mutex leave. And so we had acquired a mutex up here, SQLite 3 mutex enter, and then we released it. So a mutex is also known as a lock. And so this action of executing a query consists of taking a mutex to the database. That's what this arg is. And then unlocking afterwards. So we lock the database itself. But we may not necessarily lock the individual tables. So just because we're locking the database doesn't mean that we might be locking the tables. That might be disparate memory that's held elsewhere or whatever. This mutex is really just a lock to protect this critical section of code, right? So only one thread at a time should be doing this, basically, is the intent of that. And then we return the return code, right? And what this does is it calls these kind of inner non-snake case names that seem to do most of the kind of main driving, right? That goes from about 150 lines. We do some mallocs, get some tracing stuff for trace profile, trace X profile. Might omit explains. Sorry. Right, and I'm really trying to get to a point where B2B transfer errors happen. Yeah, so at this point, local variable RC holds the value that should be returned if the statement was compiled using the legacy SQLite 3 prepare interface. According to the docs, this can only be one of the values in the first assert below. Variable PRC contains the value that would be returned if SQLite 3 finalize were called on statement P. So it used to be a value returned back from this function, if I understand that correctly. And what it is now, if we kind of go back to where we were, to the SQLite 3 step thing, and let's go find that struct DBE thing again. And I have a feeling this is the value to return, but it's being returned as an int, which is kind of curious. Yeah, very curious. So what I want to find is void stars in the struct definitions. Right, so struct DB, go to this guy. This is a SQLite 3. Go again, here we are. And there are no void stars. There is this mem struct thing, which is memory locations. Yeah, we could go try to find this mem struct thing. There is one void star, and the reason why I'm looking for the void star is that sometimes what happens with like dynamic or generic stuff in C is void star is a way to put something behind a pointer, but kind of just pretend that you don't know what it is. And then it's the responsibility of whoever is kind of manipulating or storing or reading that data to recognize what the correct interpretation is to bring it into. And casting can go horribly wrong, right? But really most of the time you're going to have some data. Hopefully it's not a null pointer, right? And you're going to cast that data into something that makes sense, right? So maybe you have, if you go, for example, to the kind of generic implementation of quicksort in C, this qsort thing takes a void star base, and this comparison function takes two void star things, right? And the intent is that these will get cast to the right comparison in order to do their things, right? So you can provide this comparison function, and then inside of that comparison function, you can take the two void stars, which will let you pass in anything cast to those, and you can cast anything to void star, void pointer. And then once you've done your casts, because you know that this is base, right, which is your array of things. And once you know that you have casted to the right thing that's this element type, then you can do the comparison and return back an int, right, which is the greater than, less than, the ordering that we care about. But it's surprising, this RC thing, because this RC thing is fundamentally saying like, oh, well, there's this value I have, and the value to return is an int, actually. And I don't know if this is just holding, this would be a 32 or a 64-bit int, whatever, but it seems like really like one of the values to return would actually be mem. So this could be like return code, and this could be the value that's returned off of the thing. I'm not completely sure. And what I also kind of want to do, because I'm going to feel defeated if I don't do it, is let's jump back again. One more. Where were we? Go find our original place with the SQLite 3 step function. Here we go. This guy. So SQLite 3 statement is defined a few places. The in is in there, so I'm going to go to the in. I'm going to look for struct SQLite 3 statement. These are type defs. So this struct SQLite 3 str. More type defs. More type defs. It's really weird. Stood arg. How bizarro. Any case, that's that. Maybe next time we'll have a look. I think, in particular though, as a recap, we did some pretty cool stuff, which is that we found out how the opcode engine kind of is driven. And I think from this point, like, it's starting to become obvious to me that we could spend an inordinate amount of time discovering all the little bits and pieces. I think there's a couple of remaining things that I'd love to kind of figure out. So in one video, now that we've seen the prepared statement stuff a little bit, just a teensy bit, and we've seen some of the bytecode engine stuff more in depth, it might be cool to actually go back to the shell again and then say, okay, from beginning to end, what is the path of this? And see that whole round trip, you know, from input on the shell to execution through prepared statement, parsing, etc., execution on the bytecode engine, and then bringing memory back and then handing it off to you, right? So yeah, hopefully that was cool. That might have been a little bit more, I guess, deep and gory than the other two have been. But yeah, I look forward to going to the next one.